Hello everyone and welcome to the video. So in this video we're going to go over the basics of F# and functional programming. We're actually going to start pretty slow, pretty slow. We're going to move forward and we're going to incrementally go towards more advanced topics. Now to make this video manageable in terms of not having to explain the whole, like everything, I'm going to assume you already know how to program. You already know one programming language. And knowledge of object-oriented, at least the basics, is very encouraged. So I'm assuming you know what an interface is, you know what a class is, instance, you know what static means, you know that kind of stuff. And I think it's it's reasonable to assume that it's going to be a lot easier to communicate a good amount of information to a good amount of people, not going to the both extremes. So let's start with a few definitions. Let's start by defining what functional programming is. And to be honest, it's kind of hard to define what functional programming is. But the best definition I could find is that functional programming is a process of building software by composing pure functions, avoiding shared state, mutable data, and side effects. So let's unpack that a little bit to make it more, more understandable, more human-friendly. And let's break it down to two categories of definitions. So there's a first part, which is composing pure functions, and we could also include side effects in that. And there's another part where we try to avoid shared state and mutable data. So what do we mean by avoiding shared state and mutable data? Well, first, we have to define what state is. State is all remembered information in a system. So it can be variables and stuff, it can be anything, but it's remembered information. I think probably if you already program, you know what I'm referring to. Why do we want to avoid shared state? Well, it's very error-prone when multiple systems have access to the same state. It makes things not deterministic, meaning that the things you do are the result of, let's say a function or the result of a system will depend on its state. And that does make things less testable, and it can cause errors that you wouldn't have thought of previously. It's also not optimal for concurrent programs, because concurrent programs, that's exactly what I just described as many programs or many threads or many processes are trying to access a piece of data. And if that data can change, well, that can cause issues on any of the processes of threads. So what does it mean to compose pure functions and to avoid side effects, which is the second part of our definition? Well, let's start by defining what a pure function is. So a pure function, by definition, returns the same output for a given input. So if you give the same input to that function, it will always give that output. That's the first component of the definition. So it is deterministic, which is the word we use. It's deterministic. And the second part is that it has no side effects, meaning when you execute that function, nothing else in your system will change. So no state elsewhere will change, or nothing will be printed to the console, or there will be no web requests done, or no request to the database. It's a mapping one-for-one between the input and the output, so always the same, and nothing else is going to change in your system. So as I mentioned in my first video, F# is a functional first programming language, which means it supports other paradigms. It supports object-oriented programming, and it supports imperative programming. But by default, it encourages functional programming. So even though it supports those two other paradigms, I'm not going to be talking about them in this video series, and I'm not going to be showing you the features that will enable you to program in those paradigms. I'm trying to focus on really what will make you the best developer, and I believe that will be focusing on the functional aspect of F#. So even though we can do interfaces and classes, we're going to maybe talk about it a little bit, but we're not going to go too much into depth in those concepts. Also, if you're coming from an object-oriented background, the biggest challenge for you will be to unlearn a lot of the concepts from object-oriented. So mainly like encapsulation of data and the encapsulation of state and inheritance will be the two biggest things you want to unlearn. But you don't have to worry though, because abstraction, polymorphism, and composition are concepts that are very encouraged in functional programming as well. So you don't lose everything you've learned. Another critical distinction to make between the two paradigms is that we're going to actively seek the decoupling of data and behavior. So in OOP, you would have your data encapsulated in your classes, and you would have a behavior that interacts with that data. But in functional programming, we really want to separate the two, and we create pure functions that act on data and returns new data. So that's one of the key shifts to make also. All right, so to run and write F# code, you need to get started with your development environment, and you can check out my last video where I go through all the developer setup to make either Visual Studio, JetBrains Rider, or VS Code. I have all three setups shown. Today I'm going to be using Rider on Windows, and we're going to be using the .NET Core SDK for our runtime. All right, so without further ado, let's get started. All right, welcome back everyone. So I'm at the computer now, and we're about to learn some F#. So where I'm at right now, I'm in my Rider IDE on Windows, and I'm basically at the point where I left off in the Getting Started video, which I mentioned in my intro, to get set up and create a new empty project. So I have an empty project here, and that's basically where I'm going to start today. This video is going to be more of a kind of a conversation live stream kind of video. I'm going to go step by step. I have a kind of a checklist of everything I want to cover, and we're going to walk through all those foundational concepts of F#. To start, what I'm going to do is I'm going to create a new file, project, new file, and it's going to be a script file. So it's going to be a .fsx. I'm just going to call it tut1. It's going to be the first file we're going to do. And once I've done that, I'm actually going to delete the program.fs file. And just because we don't really need it for now, and I want to show you the concepts to lead up to that, hello world program. So we have an empty file here, and we should probably explain what's the difference between a .fs file and a .fsx file. The .fs file is going to be your normal source file, so it's basically like a .csx file, or a .cs, file in C#. It's basically where you put your source code, and you're going to be dealing with those kinds of files all the time. But the difference between the .fs and the .fsx file is there's going to be different compiler warnings between the two files, and you can so the .fsx file is more for scripting and using the F# interactive window, which is where we're going to use to learn. For now, we're just going to create a new fsx file, and we're going to write down the most basic instruction we can find. We're going to basically talk about the let command, the let binding, as we call it. In any other language, it looks like a variable declaration. I'm actually going to call it different than one. It's going to be very confusing. My1 is equal to 1. So what does this mean? Well, the let binding, what it does is associates a value to a name. So we're associating the value 1 to my1. It's pretty straightforward. In other languages, this would be declaring a variable, but it's very different in F#. Let space my1 equal to 1. So a few things here. Firstly, you don't see a type here. We're not saying my1 is an integer, because the types are inferred in F#. So the compiler looks like the value and determines what the type is, and then it says, okay, this is an int, so my1 is an int. And this is the IDE, basically. You see the int here. This is because in Rider there's a code lens, I believe it's called. Code vision. It'll show you the type of what the name represents. So in this case, just saying that my1 is an int. It's very helpful, and it's present in all the three main IDEs in Visual Studio and Visual Studio Code and Rider. So that's pretty helpful. The second thing is that there's no semicolon, so I don't have to do this. So in F#, your expressions are separated by whitespace. So if I do my2 here, compiles, it's fine. Also, I said compiles. F# is a statically typed compiled. It's a compiled language. It's not interpreted. Obviously, it's like C#. If you have to use multiple lines for your declarations, use a new line here, and it uses indentation to determine what your expression is. For variables, for now, you can just keep it on one line. let's talk about how we evaluate this. The F# interactive is where this comes in. Since we're in a scripting environment with the .fsx file, we can actually select everything, and depending on what IDE you're using, you can set it to the F# interactive window. And what this does is it can evaluate it can evaluate instructions without needing to compile the whole program. So there's a executable called fsi.exe, and I believe in .NET Core it's actually not fsi.exe, it's actually a command in the .NET CLI that's called .NET space FSI, and we're going to use that to interpret, I guess it's interpret the commands, since we're not really compiling. We're sending it to an executable, which it will execute it. So this is more interpreted, I guess you could say. So we can send a selection with this command, the control \. I'm going to be using that. In VS Code, it's Alt-Enter, I believe. It will differ depending on your IDE. So if I select this and I send it to, I just evaluated the last one. But okay, here you go. So by selecting it, I send it to the F# interactive, and it tells me that I have a value called my1, which is an integer. So this is the type annotation. We're going to talk a little bit more about it. And it says it's equal to 1. And now it says my2, which is an integer, is equal to 2. So basically it evaluates the expressions that I'm sending to the interactive. It leads me to talk about the type annotations. So even though F# is a type inference language, you can still add type annotations yourself, and this is going to be useful for different reasons. The first one is if you have a more complicated type, you might want to specify just to make sure your code is returning the type of value you really intend to. So let's say if I want my 1 to be a double, I can just go two dots and do double here. And now it's going to say, hey, this expression was expected to have double, but here it's int. And normally in C# this would be fine. You can set 1 to be a double, but in F#, because of the inference engine, and it would be a lot more difficult to allow those implicit conversions. So in the F# language, you can't implicitly convert an integer to a double. I think in this case, it can be seen as a negative, but it's not the end of the world. You can just add a dot, and the literal will be interpreted as a double. Since F# is on the .NET framework, .NET Core also, it's in the .NET ecosystem, so you have access to all the primitives and all the types of the system namespace we're using .NET. If you've never done C#, don't worry about it. It's not a prerequisite. But let's say you can have hello is equal to hello. See, it says there's a string. So a string is a sequence of characters. You can do a character. So let letter A is equal to letter A. Okay, good. We can do a Boolean. Okay, it's pretty self-explained. So let's say I want to set enable to false. So normally in any other language you'd probably go do is enabled equal to false. Now this compiles, but there's a big problem with this. So if I evaluate all this, say is enabled equal to true, and val it is a boolean and it's equal to false. So there's no it, like what's it? I didn't specify any it. In the F# interactive, when you evaluate an expression and you don't give it a name, the last expression you have in your file, in this case is enabled, and it's equal to false. So it is actually the evaluation of that expression. So it says it is equal to false, but I don't understand why is it saying that is enabled, but why is this false? It's because in F#, the equal operator is actually equal in other languages. So it's an equality operator. In F#, you don't change the values. You don't change your let bindings. You don't change the values of your let bindings. It's because by default, it's immutable. So I can't go and change the value of is enabled. The operator to do this in F# is this. So this is me trying to change the value of the is enabled like placeholder. It says this value is not mutable. Consider using the mutable keyword. Let mutable is enabled equal to expression. So I can actually put the mutable keyword here, and then it will allow me to mutate that value. So now that we know that we can mutate values, we're never going to do that again. Like literally, not literally never, but very sparingly do we want to use mutable values. It's actually the premise, and that's why it's the default of F#. We don't want to encourage mutable values because it's error prone, and it's actually the basis of functional programming. We want immutable logic, we want immutable data, and we don't want to mutate values. So when should we use mutable values? We should use it when it's very performance critical and there's a massive advantage of having that mutation. In that case, you would still want the signature of your function to be, you would still want your function to be pure in the way that it will be pure, that it will always return the same result. You always want it to be deterministic, and if it's not deterministic, well, we have strategies for that as well. But for the purpose of this tutorial, we're not actually going to look at the mutable keyword, and you should never use it while learning functional programming. You should literally never use it. Always find a way to have your logic immutable. Most of the time, like literally 99% of the code I write is immutable. And maybe that 1% of times where it is mutable, I'm either using an actor, which we'll talk about eventually, or it's test code. So in test code, if you're faking external dependencies like the console, maybe mutable value is not that bad. Let's look at functions now. So a function, let's go add x and y is equal to x plus y. Functions use the same keyword as the values that we declare, or variables. They're not variable, but you can think of them as variables. And why is that? Well, in F#, functions are values. So that's a big thing. Functions are values as well. They are first class values. They are things that you can pass around. You can give to other people. So it makes sense to use the same keyword as values that are of types, simple types or primitives. The second thing is that the signature, let's look like the code vision is what it says here. It says, I have a function that is int, arrow, int, arrow, int. Well, let's do a simpler function first, and then we can move from there. Let's go add 5. X is equal to x plus 5. So this is int, arrow, int. So what does that mean? It means that I have a function that takes an int and returns an int. So it's pretty self-explanatory. You can just say the arrow is the keyword return. The other thing you'll notice is in F# you don't have to use the return keyword. It's just the last line of an expression is what you return. It's the return value. So that's the last line. Let's say this 5 expression is a little bit more complicated and I want to put it a let binding. So if I go 5 is equal to 5, I can actually use 5 here. So the let keyword can be nested. The last line of the expression is the return value. Also, if I just put 3 on one line, it's not going to do everything. There's a warning here. F# is an expression-based language. I've been using the word expression, and maybe we didn't talk about it yet. But let's compare a statement-based language like pretty much any other object-oriented language out there, like Java, C++, C#. These are statement-based languages, and so the instructions are not values themselves. So in F#, I'm just thinking of the let keyword that doesn't really return an expression, how it's commonly used. Most other instructions are expressions themselves, and expressions are values. So that's why I said a function expression is a value. You can give it to someone else. I have the expression here. This is a constant expression, so constants are expressions as well. So there's an expression of 3. But I'm not really doing anything with this 3 value. So the compiler tells me, hey, the result of the expression, it's not being used anywhere. What's wrong? Like you're doing something that's not correct. It compiles, but it's not a good idea. Just to show you that the last line here, I have a value and it's being returned, it's being used, but This one's not being used. Every new line is an expression, is a new expression. And so normally in other languages you use the semicolon to terminate statements like this. And that can actually be done in F# as well. Like this is two expressions. So you can use the semicolon to delimitate statements, although we never do. Only in certain circumstances like lists. So what happens here? It takes an int and returns an int that returns an int. Let's look at multiple ways of expressing this expression, and we will dig a bit deeper and look at why it's written this way. Add prime, and let's make it equal to fun x, y. Okay. These two expressions are exactly the same. The fun keyword is the keyword for a Lambda expression, an anonymous function. They are common in basically any language like Python, JavaScript, C#, Java. I think most languages have them now. So I'm assuming you know what a Lambda expression is. It's an anonymous function. So it's a function I can pass around. Normally in C#, you can't really pass around functions. Like, you declare a function. Well, you can. It will actually, do a delegate, and so delegates are lambdas, and lambdas are delegates in C#. But in F#, there's no really discrimination between what a Lambda expression is and a function is. Let's look at the third way to look at this expression. So if I go let add prime is equal, and this will take one parameter. It will return a function that takes one parameter, and it will turn x plus y. Okay. So again, all of these three have the same signature. In this one, this is basically, there's a technique called currying, where we're baking in. And what that does is basically you bake in a parameter, in this case it's x, and you bake it in to a function, in this case it's x plus y. So what that does is you can give a parameter early, you can give a function a parameter, and it creates a new function that takes a parameter. So instead of having a function that takes two parameters, now you have a function that takes one parameter, and it returns a function that also takes one parameter that returns the result you actually want. And this is a strategy that's very common in functional programming, where the mechanism to inject dependencies is through this baking in, and it's also called currying. Currying is when you create a function that returns another one, That's basically currying, where you're creating functions that take one parameter and return one value. Instead of having two parameters, and you absolutely have to give two parameters to call the method, you only have to give one, and then you get a new one. So that's basically called currying, and in F#, all functions are curried. So all functions in F# are curried. So it's exactly, this is actually, behind the scenes, it's actually written like this. So it's actually written as a one parameter function that returns a new function. That's why this is the signature. It's basically, if I go here, it's basically saying I'm going to take an int and I'm going to return a function that takes an int and returns an int. So this is a basic function declaration, and this is a new function that returns a new function. If you see two arrows, it means it's a function with two parameters. You don't have to think about it this way. This will kind of maybe confuse you. In C#, the signature for a func in F#, in C#, sorry, if your func takes a string and an int and returns a string, the type signature will be func string int string. So the way you read it is the last one is the return value, and then all the other ones before that are parameters. So that's basically how you can look at this function signature and say, well, the last one is the return value, so I know this returns an int, and it has two parameters that are integers. I'm spending a lot of time on these concepts because they're basically the base of the language. If you don't, if you have a hard time understanding this, it might cause trouble in the future. So I really want to take the time. And even though some of you might have understood like 10 minutes ago, I'm gonna still take that risk. So now that we understand the concept of currying a little bit, or at least conceptually, we'll look at how it's applied, but conceptually, we can talk about partial application. Let's say instead of this implementation of add5, I can rewrite add5. So there's two ways I can do it. I can do add5 that takes a parameter, and I can call add x and 5. So what I'm doing is I'm calling the add function here, and I'm passing 5, and I'm passing the parameter that's being passed to me. Okay, pretty self-explanatory. And by the way, I feel I didn't cover enough time with the parameters of the function. It's a space-separated list, so normally you would use a comma to do that. So in other languages, if you want to specify the type of a parameter, you have to surround it with parentheses, like this. If you do it at the end, it's not actually going to say that, in this case, it's not going to say that y is an int. It's going to say that the add expression is an int. One thing to keep in mind, that's a newbie gotcha. If you want to say that the y, let's say string, so it's going to say, hey, this whole expression is supposed to return string. So if you want to do it on y, you have to surround it with parameters like this. And most of the time you don't have to do it. But for C# types, or like .NET types that are implemented in C#, because with the dot notation, when you access something, let's say this was an object and you do dot to string, it doesn't really work. Like it's hard to infer what it is. But with F# type methods, it's really easy to infer what it is. So let's go back here. And when I'm calling the function, I'm giving also the space-separated list that we talked about. So we gave two parameters to the add. It's going to do add plus 5. So if I evaluate this, I'm just going to evaluate this in the interactive window. And now I can go add 5 prime. And if I give it 6, it should give me 11. All right. So it is 11. Good. So another way I can write this function is like this. So it tells me the same thing. It tells me it's the same thing. So add 5 is equal to add 5. But I'm not giving add all its parameters. It's asking me for 2 parameters, but I'm only giving 1. This is called partial application. Basically, the word application, when you apply something in a functional programming language, it means that you're giving a parameter to a function. So if you're partially applying, it means that you're not totally giving all the parameters the function wants. So what does this do? Well, it takes my 2 parameter method and returns me a 1 parameter method. It's very succinct. I don't have to write everything out, and I don't have to do x and then pass x here. That doesn't mean you should never do that. In this case, this would be a point-free implementation. And point-free means that we're not specifying all the arguments and parameters that are being used. We're leaving some on the table, and some things are incomplete. So we have functions. What do we do with them? We can actually combine functions together. So it's a very powerful thing. So let's say in this example, I have a math operation. So in math, I have a number, and I want to do plus 3, and then I want to multiply that result by 2. And then I want to do the power of that result to the power of 2. You can actually just directly copy this if you want. So let's say let operation. So this is the operation I'm talking about. And I have a number, and it's going to be equal to this. This is actually not the power operator. This is the power operator. And this doesn't work because it's expecting the exponent to be a double. So we're just going to put a dot here. The type int does not support power, so this expression needs to be an int. It needs to be a float, sorry. And we can do that by doing this and this. Great. So this expression takes a float and returns a float. It can also be doubles. I mean, doubles is just a float that's double its size. In math, this is not the end of the world, because in math, it's basically, you use parentheses to you have an order operation that's already established, and you can use the parentheses. But in programming, it's really nice to read the order instructions in the order that they're going to be executed. So in this expression, the order of execution is going to be this number plus 3, then it's going to be the times 2, and then it's going to be the exponent. Ideally, that's not what we want. We would want to see the number plus 3, and then the multipliers by 2, and then the power of 2. I want to write down each of these 3 functions. So there's 3 functions here. There's the add 3. So I'm going to show a neat little trick here, actually. I'm going to take a little detour. And I can do number plus 3. But in F#, operators can be called as functions. So this plus, this is actually called the infix notation. It's infix because it's in between the parameters. So it's infix, but you can also use the prefix notation, which is the operator, and you surround it by parentheses. So this is the same thing. And why do we want to do that? Well, now, if I inverse the order of these 2 things, what do you think we're about to do now? We have this number that's being passed, and it's being passed at the end, which is clearly a sign that we don't have to specify it. And that's exactly what we're going to do. So we're going to remove this, and remove number. All right, so this is very succinct. I don't really have to write a function for this. It's very nice. And one thing to keep in mind is that I'm just going to Control Z. This is the same thing as saying 3 plus number. So the first parameter passed is the one on the left. And the reason why I say that is because it can be confusing since it's on the right of the operator, like here, the 3 is on the right. So if I write the new add 3, that's right here. This actually translates to 3 plus number. So even though the 3 is on the right, it can be confusing to see that. But for the plus, it doesn't really matter. It's a commutative operation. So no matter the operator, or no matter what on what side the plus is, it doesn't matter. It will turn the same result. So that's fine. But in other operations, you can see that if it was a division, so if I was doing this, well, this is my nominator. Is that the word in English? I'm not sure. Nominator. It's not the denominator. So that's one thing to keep in mind. So I'm just going to go back with my add operation. I'm going to do the same for multiply. So this is multiply by 2. So times 2. And I'm going to do power. So pow 2. Or square. Yeah, square is kind of not a good word because it'd be square root. So I'm going to just say pow 2. And in this one, this is where you have to be careful. That's kind of funny. This is the, you can do a comment. That's actually how it's written. It's parentheses, asterisk, asterisk. So I think you can escape it. So you can use spaces, which is like that. And all of these need to be floats. So in this case, it's kind of not a good way to write it because, so the 2 is the number that's going to be multiplied. It's not the multiplier. It's not the number of times it's going to be multiplied by itself. It's going to be the, so this is basically writing 2 to the power of x. It's not x2, so that's not what we want. And this is the case where you want to specify the number here. So you can do 2 dot and remove these, and then you're going to do number. Actually, that's not, no. In this case, that's not what we want. That's exactly the opposite of what we want. All right, so now we have our 3 functions, and normally what you would do, you would go times 2, so you plus 3, and then you go this, pow 2. Okay. So this is not really a nice way to write it. It happens pretty often when you use the parentheses and you want to compute a value and then give that computed value to another function. that's normally what happens. So the way you normally solve it in other languages is you write temporary variables. So let add is equal to 3. And then you go times, it's equal to times 2 add. And then you can do pow2 of times 2 at times. So pardon the bad function names, but I'll just go x and y. This is y. So that's basically how you'd solve that readability issue in other languages. But in F#, what you can do is you can use function composition and just composing functions together. So in this case, basically we have a function that goes float to float. So that's the add plus 3. And then we have another one that goes float to float again, which is a times 2. And then we have another one that goes float to float. So this is a perfect opportunity to compose these functions. And there's two main ways I want to show you how to compose functions, but there's a lot of ways. So the first one is with the pipe operator. So all of this can be rewritten as number, and you're going to pipe that into add 3 prime. So this is exactly the same thing as add 3 prime number. So I'm basically giving number and I'm applying it to the expression on the right. So this goes normally left and right. So it's always in the infix notation. And you give the expression on the left and you pass it to the right. We do add 3 and then we do times 2. And then we do pow2. This is much more readable than the other two ways we wrote this function. Maybe for math, maybe math is a strange example because we're used to this notation, but it's hardly impossible to argue that this is less readable than the other ways. And readability is really important in code. I feel it's the most underestimated parameter of what good code is. Good code is someone else can come in and read what it means very easily, and it's maintainable. And those aspects are very well encouraged in F#. There's a lot of things that make reading easier. And don't get me wrong, there's a lot of people that go overboard and create new operators that are frankly unreadable. And we're not gonna go that route. We're gonna use terms and operators that are understandable in the natural code base. And of course, if you're a newcomer, it's going to take some time to learn those. But this is why I'm here. I'm trying to bridge the gap and make the learning a lot easier. So this is the first way of doing it. So we pass the number to add 3, and then the result of that is being piped into times 2, and then the result of this is being piped to pow2. If there's the operation in the middle I'm not going to use anymore, well, we can just remove it. It's very easy to modify and add stuff like this. It's a chain, and it really models what functions are supposed to be. Functions are supposed to be pipelines of data. So you have data coming in, and then there's logic, and then you have data coming out, which is a principle of functional programming. Like we talked about, we want to decouple the data and the behavior. The second way of composition functions is with the function composition operator. I believe that's actually the official name, so guess what it's used for. Let's go operation prime prime, and now we're not gonna pass the number. Instead, we're gonna do add 3 prime, pipe it into times 2, and well, it's not actually piping it. We're gonna compose pow2. Okay, this is not cout. In C++. Let's first look. They both have the same method signature, and let's just we didn't evaluate these yet, so let's go ahead and do that. So I'm going to pass it into the window, and I'm going to go operator prime of 1. Has to be a double. So it's 64. What is the result of the second one? It's supposed to be operation. So what's the value of this? I have to send it to interactive. So if you change the method, you have to resend it to the interactive window. So the last time I sent it, it was called operator prime, and I renamed it, so I have to repass it. Okay. So both of these values are 64, so they are equivalent. Let's actually do the implementation of this operator so we can understand what it actually does. So if I was to implement this operator, fun, and, oh, that's fun, let, and to define new operators, you do it this way. So let's say I do this. It's going to take two functions, right? So this is two functions. There's a function on the left, function on the right. Okay. This will return me a new function, x, that takes an x. So basically, I'm going to do a lambda expression that takes one parameter, which is called x. I'm going to do x, pipe it into f, and then I'm going to pipe it into g. In other words, I'm doing fx, well, I'm going to put the comment here. So this is what I'm doing. I'm doing fx, and then I'm getting the result to g. So this is a clever way to compose stuff together. So between these two implementations, which one is more readable? You know, in this case, it's not too bad. Like, it's not too bad to say add 3 times 2, pal 2. But normally, if you can, you want to use the piping, the pipe notation. This is point-free code, which means there's an argument here, like operation, it takes an argument, but I don't see it. I don't see it, and thus it's less readable than this. So the recommendation is use point-free code where it's nice and readable. And, you know, this is actually not that bad. It's actually not that, you know, it's not like, oh my god, I don't know what this does. You know, add 3 times 2. Normally we'll prefer this along the series. But these are actually how you can compose functions together. No, we actually didn't talk about a lot of concepts, but we went very in-depth in them, and hopefully that time investment of talking exactly why we do these things and why we should do them, hopefully it will pay off. I'm fairly confident it will. But for now, this is a checkpoint basically in our learning, where we're ready to talk about other topics. Now I want to talk about more the structure of an application a little bit. Not really into depth, but what are the basics, like the complete basics of what a .NET application is, or an F# application in this case. So I'm going to create a new file. I encourage you to do so if you're following along. I'm going to do tet02, and this is going to be a source file. And see, there's already a big difference between the two files. It's asking me for extra information at the top. I'm actually going to remove this, and I'm going to do namespace. And then my project is called F# Basics, so I'm going to call it F# Basics. If you're familiar with namespaces in .NET or in C#, basically the same thing. Well, it's exactly the same thing. So namespaces are, and then I have a really cute definition written down. So to be honest, it's pretty simple. The namespaces are groupings of code that are grouped together by a name. In this case, this name is F# Basics, and basically everything in this namespace will be qualified with the name F# Basics. It's the same concept with packages in Java, and namespaces in .NET, namespaces in C++. The standard namespace. I don't think I have to explain too much in depth for that. So what's a module? A module it's actually implemented as a static class, but you can think about it as a piece of code that contains code elements in it. So it's a grouping of code elements, and there's a few differences between the two. The first one is I can't have values in in namespaces, so I can't do x equal to 1. It'll tell me namespaces cannot contain values, so no let bindings here. Basically, namespaces are good ways to contain classes and modules, or types, classes and modules. Obviously, classes, we're going to use less of those in functional programming. We're going to use more types that we defined. But mostly, we're going to be putting our code into modules types are often not in modules. The other thing we can do is we can have nested modules. So I have this module arithmetic as a a test. I can do module addition, and I can do define a function here. Let add. I know a lot of you are probably sick of my too easy examples. You're kind of craving for more, but we're gonna get there. I have a function in a module called addition, and that module is also an arithmetic. It's not really like super standard practice. I'm just saying it's possible. And now if I want to use the add function in another module, let's say I'm in another module here, I can do let my program is equal to, I have add 5 plus 3. And now it's going to say, hey, I can't find, I don't have add, I don't know where it is. So first thing you can do is you can qualify it. So you can say that this is arithmetic.addition.add. The second thing you do is you can open a module and namespace. So I can open arithmetic, and now I just have to go addition.add. I can also add both of them. In F#, code is ordered. It's read from top to bottom. If I bring this and I bring this to the top, it's going to say that my namespace module is not defined because it goes top to bottom. And there's a lot of reason for that. Firstly, it prevents cyclical dependencies. It's like you can't have cyclical dependencies if all your definitions are ordered. It looks like a painful thing, but it's really a great thing when you get used to it. In C# you can get away with it, and that can create cyclical dependencies. So we don't want that. Files are ordered as well. Let's say I have another file here. It's going to be a source file. Use other stuff. And I don't really care about this for now. So if it's on the bottom, I can open the other module in F# Basics. But I can actually move the file up in my IDE. So most IDEs support this, the Visual Studio and Visual Studio Code. And if I move up, it's not going to find it. So namespace is not defined. And this is all a mechanism to prevent cyclical dependencies and just better practice. In other languages, you can like hear this and think, oh my god, like how am I going to survive? I have to order all my files. But file count in F# is very, very low. It's probably the lowest I've ever seen in any other language. Probably other functional languages are also very succinct languages, so I'm not going to say it's more succinct than other other functional languages. But compared to object-oriented languages, it's completely insane. And we're going to do the example application and in a video or two. And well, you'll see the comparison in 2 videos. It's night and day. It's completely not comparable. And it's actually not a bad practice to put a lot of your code in the same file if they're separated by modules. You would think that you want to hide the implementation and encapsulate the data, but functional programming is not about that. We're not about hiding the mechanism in the object. We're about pure functions that return the same value and don't mutate stuff. So you don't have to hide those implementations, or like you don't want to have coupled code, and you don't want your logic to be coupled to an implementation, but seeing the implementation of something is not a big deal. It's much better to see a lot of your code in the same file. Navigation is a big thing, and if your code is all over the place, I mean, if you've worked in any project that's very well decoupled, it's not even. It can be a pain. Obviously, ReSharper. Now, I used a lot of ReSharper in my use. That's why I'm a big fan of Rider, because it's made by the same company, JetBrains. It's very difficult to find code, and they have a command to find everything. It's a Control-T, and you can find a lot of stuff with that. But if you don't have that, it can be it'd be a complete hassle. This is actually a great thing, in my opinion. This is very opinionated. And if you're used to it the same way, like you put an interface in the file, and then you have a class in the file, and all your files have one thing in it, it can be a clash. It can be a clash of belief system. But I recommend you try this approach, And we're going to look at examples of a enterprise application, or enterprise-ish application in C# and an example in F#. And you can decide for yourself which one you prefer most. So I'm going to use the namespace at the top, and you should always be using namespaces at the top of files. The reason for that is basically you want namespaces to contain a lot of modules. You preferably don't, like, modules shouldn't always be nested. That's another thing. And it's just the .NET practice. It's more of a .NET convention of having modules at the top of the file. So that's basically that. And before I move on to the next topic, I just want to go back here, and there's a few things I wanted to explain. Firstly, in modules, the let binding, you can associate a privacy accessor. So it can be private. You can say that the let function is private, and it'll tell you it's not accessible. These behave the same as languages. So private means it can only be used in this module, but it's public by default. So you don't really have to specify it. It's just implied. Modules can also have privacy accessors, so a module can be made private. So it means that only the arithmetic module can have access to the addition functions and members. Let's look at a main function, and we have a console application here. You probably have a main function eventually. So to have a main function, you have to have a module. Program is equal to, and then we have a main args, which is basically a signature of a main function. There's a few things that differ from other languages. The first one is the main function needs to be decorated with an annotation called entry point. So annotations are the same annotations in .NET and C#. They're similar to the annotations in Java. And in C# you add the square brackets as well. So it's square brackets and angle brackets. Entry point. So entry point is to say that this is a function that's an entry point of the application. It needs, so here you can see it has a specific type signature. So it takes a string, an array of strings, and returns an int. So the int is the error code of the program. Normally it's 0. So you just put 0. If you create a new file, or if you create a new console application, you'll get it built in. But we deleted the program.fs file because I wanted to explain everything from this point. We can just run it. It'll do nothing for now. So the way you run it is you can probably do Control F5 and run it on Writer and Visual Studio. On VS Code, you have to use the terminal. I usually use the terminal with the .NET CLI because I just prefer learning the commands. So if I go on my laptop, which is on Linux, I can use it. I can use it from here also. But I feel a good understanding of the .NET Core CLI is very practical for developing. I'm in the solution. So I basically have a solution, and I have a folder. And the solution is the solution in C# as well. If I go F# basics, which is my project, and I can go .NET run, it'll compile the code and execute it. So it'll build the code and execute it. There's also the .NET, and you see it does nothing because there's nothing here. And before I want to add a printout, I actually want to talk about a data type that I did not talk about, which is the unit data type. And unit is this thing. I want to just recall that if I add a value on a new line, it'll underline and say the result of this expression as type int is implicitly ignored. Since values and functions in F# should be pure most of the time, their return values should be used. Because you're calling the function, you're giving it something and getting something in return, so you're doing work, and you should do something with the result of that work. If that's not the case, it means your function has a side effect. The side effect, as we talked about, is a change in the system or another system. The function signature is not good, because it says that it's taking something and returning something, but it doesn't really define, or it doesn't really show that there's a side effect happening. And that's where the unit type comes in. The unit type has two main, it's seen in two main or three main occurrences. The first one is when a function returns unit, it means that it did something and something changed. A common example is the print function. Console write line. It's a function used in C# to print to the console. It's equivalent to system out print line in Java. I feel everybody has a pretty good understanding what it is. It's the printing function, so this is like go hello world. I can run this in my terminal. And this, let's look at the function. It takes a string and returns unit. So unit is basically void. You know, it's a void method. Void in other methods, but we call it unit in functional programming because it's not exactly the same thing. It's represented for the same reasons, but it has a different function in some occurrences. So another convenient way you can write this actually is you don't have to specify the parameters in F#. So that's nice. You can use it as an F# function. So all .NET functions that are written in C#, you can use them as F# functions like this. So if I do this without this, we can run this. So the first reason to use unit in your function signatures is when something changes or when there's a side effect in your system. And while we're on the topic of console write line, this is actually not the way we print stuff to the console in F#. We actually use a function called printfn, or printf. So I can say hello world. So F stands for format, and it's, you know, there's printf in C and stuff like that. I think there's a printf in C. I haven't done C in a while, I'm fine, but it's a formatter. So you can add placeholders, or let's say I want to print a number. So hello world, and I am going to just put 26 here. Well, obviously this doesn't make sense. I would just write 26 directly in the string, but let's say I have a variable. It's equal to 26. I can just put it here, and I can do it like this. If I run this. So the first thing, why is this cool? Well, I can format my string. Okay, that's fine. Great. But that's not really that cool, because I can just use string interpolation if I wanted to do that. But the really nice thing is that it is type checked. So it's expecting a string, but it's an int. So %s is a string, so s is string, I is integer, f is float. Why is it that cool? Well, it's basically for that. It's not, it's just the function we use. And printfn will add a new line. How can it do this? How can passing a value into a string, how can it give me a compiler error? There's a lot of functions in F# that have integrations with the compiler to give you design time errors. So what does design time errors mean? Well, so you have compile time. So that's the time of compilation, and there's a lot of type checking going on. For a compiled language, that's how it works. Normally, it's where you have a build, you have build errors, you fix the errors, and you're good. And then there's runtime errors. So there's compile time, and there's runtime. At runtime is your code compiled, but let's say you divide a number by 0, and that will give you a runtime error because the types, the types work. You can divide an int by an int, but you can't divide an int by 0. So it will give you a divide by 0 exception. That's a runtime error. What is a design time error? So design time refers to at the time of writing the code. So it's even prior to the compilation step, and it's mostly with the tooling. So the tooling helps you. There's a lot of integration with the compiler and the tooling in F# for most IDEs like Writer and Visual Studio, and so that's why we use it. Okay, so we saw unit used as a return value, but what about unit used as a input value? So another common one is console readline. So let's look at my example. I'm just gonna ask, I'm have a prompt, and we're gonna do, hi, what is your name? And we can do this. We don't need a new line. And then we can look for the console read line. So we can read the input, basically. And so let name is equal to readline. So readline, same method as in C#. It basically will get the input in the string, and it'll put the string in name. You see here, you had the parentheses. And normally in languages, that's how you call a method, is with the parentheses. But empty parentheses in F# is passing unit. So you're giving unit to a function. Why would you give unit to a function? Firstly, it's when your function is not deterministic. So pure functions, you can think of them as a mapping. It's a mapping of a certain set of inputs to a certain set of outputs. Let's say 2 plus 2, or x plus 2. You know, if you have a function called, let's do it here. Let x plus equals, or 2 equals x plus 2. You can think about this as a mapping of, if I have 1, it returns 3. If I have 2, it returns 4. If I have 3, it returns 5. So you think about it as a mapping of two values. And non-deterministic functions, you can't really think about it that way. Yeah, if you give something, you might have something else in return depending on other factors in your system. In this case, it's depending on what the user enters. So that's why we use unit to explain as the code and say, this will not return the same value all the time. So that's a very big distinction in the semantics of the language, where you can read and see what is deterministic and what isn't. And that's the thing that even if you write functional programming in C#, you'll never get that benefit. So now name has a value of what I prompt in the console. So now I can print out, and I can go, hi, %s, and oh, I forgot a T. There you go. And then I can give it name. That's great. And let's say I have two things to pass. I have two parameters to pass. It's a space separated. So this returns a function with the number of parameters equal to the number of things I pass here. Just an FYI. And so I can go name again. And I can pause. But we're just going to do 1 for now. If I go here, I see, hi, what is your name? And I can go, my name is Ben. And I go, hi Ben. Very good. So everything works here. I said there's 2 reasons, or 3 reasons why we want to use unit. And the other reason, the third, so the first one is when there's a side effect. The second one is when it's not deterministic. And the third one is when you want it evaluated at another time. Because F# is a eagerly evaluated language, which means if I do let x equals 1, then it will, or x plus 1, or 1 plus 1, it will evaluate this when it's defined. So it's defined here, and it'll get evaluated. But for some things, you don't want that to be the case. You want it to be lazy evaluated or evaluated every time that you call it. Let's look at the latter in this case. So I'm going to just remove this, and let's say we want to play with time, with the datetime library. So if I go let current time is equal to datetime.now. Okay. And let's say I want to print it out. So I go print fn time is equal to, then I go %o. %o is to print out an object. So in .NET, if you're not from the .NET universe, the base class for all types is object. So everything is an object. So actually pass an int here, you can do 1, and it'll work, but normally you don't want to do that. So anything will compile basically. So I'm going to pass current time. I'm going to wait again. Probably shouldn't do this. I never do thread.sleep, but I don't want to show you asynchronous programming yet, so I'm going to use thread.sleep for 10 milliseconds. And then never use thread.sleep, never use thread.sleep, never use thread.sleep. Okay, we're good. And I'm just going to do it again. And the reason why I say never use thread.sleep is because it blocks the thread. You would want to use async or task delay if you're from C# and async sleep. But we're going to get back to that in another video. So here in this code, I'm expecting current time to be delayed at least 10 milliseconds after I wrote this. All right, let's do 2 seconds just to see, because that might be correct. Then, so 3, and then it's not 3 anymore. Or it's still 3, I should say. So this is a problem. That's not what we want. We want to get the current time. So why is it doing this? Well, datetime now is implemented as a property in C# on .NET. It's a property with a getter. The problem is, you see, there's no unit here, but it's not deterministic. So that's another smell of object-oriented languages like C#. You can have properties that are get-only, that are immutable, and you have no way to read that. If it was immutable, the value would never change, and this would be fine. If the value never changed, you never have to reevaluate it. But in this case, you have to reevaluate it, and multiple times. You have to evaluate it every time you want to use it. So the way you would signal that, the way you would communicate that, is with the unit. So you'd pass unit here, and basically every time you want to use this value, you have to pass in a unit. And you see the problem with using the O here is it always compiles, because even functions are things. So functions are objects. And you have to use the unit here. And it doesn't compile. What doesn't it compile? Well, because it's expecting one thing, but you give it 2 things. You give it the function here, and then you give it space unit. So you have to use parentheses to surround this. And then, like we previously said, you probably don't want to use parentheses because this evaluates something, and it's not the order in which it's executed. So the correct way to do it in F# is to use the pipe operator. There you go. So now I get the current time and I print it out. And then I'll copy this code and I write it, run it. Oh, I always forget to get the printout. So it's 150, 33, and then it's 35. So you see, this works great. And it documents that when I call something, it might not give me the same value. It documents the fact that it's not deterministic. And that's really a big pleasure. But like you see, there's a bit of a duty on me as a programmer, or on you as a programmer, to correctly write your function signatures. And there's a big, there's a difference between a language like F# and a language like Haskell, which is another functioning programming language. It's 100% functional programming language. And if you're going to use something which is unit, in Haskell, how you decorate or how you declare something as being impure is with the IO type. So anything that touches IO, which is input output, everything that touches that, everything that's impure will be an IO of something. And that's the way that you use in that language. But in F#, purity is not enforced because it has to be compatible with C# code. And so it's not as strict as a requirement in F# code. But you should do your due diligence and doing your best to document what is deterministic and what is not. I'm going to create a new file. So, touch4. The F# type system. We looked at primitives, but obviously in languages you don't want to use primitives. You want to build your own types and you want to make something useful to model your data. And F# type system is a very powerful one. So it's called an algebraic type system. There's two big categories of types in F#. There are product types and sum types. So let's go over the product types first. There's three main product types in F#, and I'll explain why they are product types. So the first one is a record type. The second one is a tuple, or tuple, tuple. I said tuple. And the last one is anonymous records. Why are they product types? Well, let's start by giving a basic example of what's a record type. So the record type is the most commonly used out of those two. Maybe the tuple is also very used. And the way you define it is you go type, and let's define like a person. Let's go person is equal to, the person has a name, which is a string, and the person has an age, which is an int. To explain this, I'm actually going to do another one, which is type a day of the year is equal to, so it's a day of the month, so it's like 1 to 30, so this is an int, and it's also a month. It contains a month. So to describe a day of the year, you have to have a month and a day in the month. So let's say today is April 5th, so you have April, and you have 5. And you have 12 months in a year, which is, so you have 12. You have 12 possible values in one of the fields. And in the other field, let's say every month has 30 days. So you have a set of 30 values. And the total amount of possible values of day of the year is 12 times 30 in this case. Obviously it's 365 because we have 365 days in a year. We have approximately 360. So that's why it's called the product type, because it's a product. The number of values is the product of the number of possible values of their fields. So number of possible values of each field times each other will give you the number of possible values. That's basically how it's called. It's not very important why it's called that, but I just felt you now know why it's called a product type. So, okay. Let's look at the definition. So we have the curly braces, and I have a semicolon separated list of fields. That's actually not true. It can be semicolon separated, or you can define it like expressions. They can be separated by new lines. If you have only like 2 fields or 1 field, you can go ahead and do it on 1 line. If you have a lot of like more than 2, you probably want to do it on multiple lines, which is basically the basic recommendation. So use type annotations. So there's the name of the field, then we use a type annotation, which is mandatory when you're defining a type. It's mandatory, so you can't go, like, you can't infer this. It's basically implemented as a read-only class with getters in C#, which is immutable as well. So let's look at the constructor. So if I go let Ben is equal to name and age equal to 26. Basically the constructor is kind of like the declaration, except you replace you replace equals string, you replace the type annotation with equals value. The same thing applies with the semicolon. You can put on multiple lines if you want. You have to define all of the fields. It's pretty self-explanatory. If I want to access any of these values, I can use the dot accessor. So I can do ben.name. Okay. And also notice the type inference here. It knows that Ben is a person. Let's say you have multiple fields. You have multiple types with the same fields. It will take the first one, the last one that has been defined. So let's say I have another type that's called person2. It will think that Ben is a person2. And this is one of the occurrences where, and obviously this is rare, but it does happen. So you have to just say that this is a person, and it's not a person2. So you can do that name. So if I evaluate all this, it'll say that Ben is a string, and if you do age, you'll say 26. Good. There's a lot of cool things with this that are built in. So the first thing that's pretty cool that's built in is the toString. So normally in other languages, the toString by default is god-awful and useless. So it basically prints out the hash code, and normally people really don't use toStrings on reference type objects. The cool thing is, if I go Ben, it says val it person is equal to name equals name and age equals 26. It's because the toString is actually this. This is the toString that's built in, which is really cool. There's a few reasons why that's cool. For testing, let's say, if you're running a test, so you have a value and you output it, you can see, okay, that's exactly what I want. I can actually copy this, and this is, so you can see this is actually the same statement. So the toString is actually, it prints out as the constructor of the object, which is really cool. It's actually pretty helpful when you're scripting and when you're testing. The other thing that's pretty cool, it has structural equality built in. So let's say I have another object, and this is Ben2. If you equate these two statements, or these two objects, sorry. If you evaluate this, so I'm just going to evaluate all this. So I have person2, which is Ben26, and it is equal to true. So it being this. So they are equal. These two objects are equal, even though, since these are reference types, they are not value types. So they're allocated on the heap. They're not passed in the stack. They don't live in the stack, is what I'm trying to say. Normally in other languages, reference types, they compare addresses of the references, but in this case, it compares the values. And most of the time in functional programming, you're going to be comparing values a lot more than you're going to be comparing addresses. So that's a really neat feature. And also, they have structural comparison built in. So let's say I have age 25, and I do Ben is bigger than Ben2. So Ben is bigger than Ben2 because age is bigger. So it recursively checks all its fields, and it will compare them automatically, and that's built in. So that's a lot of code that's generated. And lastly, the cool thing that is generated with the record type is there's a copy method. So I can do let increment age, and I can take a person, and I can go, this method is equal to person with age equals person.age plus 1. So this is a method that will take a person in a parameter, and the curly brace width is a copy. So it takes this instance and does a new copy of the object with a member-wise copy. So it's a deep copy. It's not a shallow copy where they just copy the references. They create new, everything gets copied over. Actually, if things are immutable, you can just copy the reference. If it's not modified, if it's an immutable, it's fine. It'll just copy it over. So it might not be a deep copy in that perspective. Age is equal to age plus 1. So I do person age and I add it to 1. So if I go and I do increment age Ben, I evaluate this. There you go. And it will give me age 27. So it'll give me a new instance with age 27. We can create new types with our types we just created. So we can do a type duo, and we can define a duo as being two persons. So I can do person 1, which is a person, and I can do person 2, which is a person. Great, so I have a new type, and that's how you build types. You know, you create small types and you build them up and you add them together and you multiply them. That's why it's an algebraic type system. So I can do a let brothers let's say. Brothers. We can do brothers is equal to, well, I can define another person. Well, let's call him Alex. And brothers can be, person 1 can be equal to Ben, and then person 2 can be equal to Alex. And now you have this. So if I print this out, if I go brothers, I'll get person 1 is equal to Ben and person 2 is equal to Alex. I get the construction of the object, which is really nice. And I can just see my data completely. I don't have to implement a toString all the time for my data. And that's very, very valuable. So there's one thing here, is that it kind of sucks that I have to create a new type for, I just want to have 2 persons. I want to have the type that contains 2 persons. I don't really care who person 1 is or person 2 is. I just want to aggregate that data. So the tuple here is where it's very practical. So I don't even have to define a new type, although I can. So I can do type duo, and do duo prime is equal to person times person. This is a type definition for a tuple. And the asterisk, like we said, these types are product types, so it's a person times a person. That's why it's written that way. But you don't actually have to define a type like this. This is only practical if you have a method and do something, and it returns. You want to return a tuple of persons. Well, you can do duo prime, and then you can do whatever. That's why you would create a new type. It's for domain modeling and to model your types. But to create a tuple, you don't have to create a type. It's anonymous. So I can just do Ben and Alex, and this will be a tuple. So it's a type person times person, and it's the 2 of them. So tuples are really useful in functional programming because since all functions are functions that take one parameter and return another, sometimes you want to group things together, or you want to deconstruct things together, and tuples are kind of like quick anonymous types that are really the glue of a lot of methods. So we'll see a lot of tuples in our future. Also, one thing to mention is it doesn't have to be the same data type. We can just put like 42 here and this still works. So it's a tuple of person to int. It doesn't have to be the same data type. I'm just writing that, and it can be multiple. It doesn't have to be 2. It can be like 3 fields, and I don't know how many. What's the maximum, to be honest? Let's try it. Okay, this works. It still works. So it can go like a long time. I've never. This is not good practice. I'm just wondering. I'm just actually wondering what. Yeah. Okay. This compiles. Okay. I'm not gonna do infinite, but you can do have a lot of tuples, a lot of fields. But don't do it. Don't do that. Anonymous records. So anonymous records are records that you don't have to define the type beforehand. So let's look at that example with two persons, 2 people. So if I go let's say I remove this. I remove this type declaration, and I'll remove this because it refers to that. So I can go duo equal to. So this is the anonymous records. It's the record with the bars. So I can do person 1 equal to Ben, and I can do person 2 equal to Alex. It'll look at this and look at this type and say, okay, duo is a person of whatever, of person. It's a person 1 of person. And this is kind of a neat middle ground between the tuple and the record type. So you don't have to define the type beforehand, which is nice. But you have the naming, so they're named, which is really cool. You can add fields to an anonymous record. So I can do trio is equal to, and then I use the same notation as the copy method of the record type, and I can do duo with person 3 And you can say, you know, let's just do bend for sake. But now I can add methods also. I can add fields, sorry, to the type or to the instance. So this can be kind of interesting in a lot of ways. But there's a pretty major downside to the anonymous record, which is it doesn't support pattern matching yet. And we haven't talked about pattern matching yet. We will be discussing it in 2 topics. So like in a few minutes. But that's not supported, and you'll see why that's a big deal. So these are all the 3 product types. So these are product types. Okay, so let's talk about sum types. Another word for sum types are discriminated unions, or choice types. So discriminated union and choices are sum types. I'm not going to be talking about choices for now. Choices are a part of something called active patterns, which is a type of pattern matching, but it's going to be discussed in another video. It's a little bit more advanced. So let's say discriminated union. Let's say you're in a deck of cards, you have a suit. You have suits. So type suit is equal. It's either hearts, or it's clubs, or it's spades, or it's diamonds. Suit is the name of the type, and it can have these possible values: hearts, clubs, spades, diamonds. Is this an enum? It is not an enum. It looks like an enum, but it's a lot more powerful. So this is a pretty simple example. And the reason why it's called the sum type, it's because it's the sum of its choices. So in this case, it's pretty simple because you have 4 cases, and each of the cases have 1 possible value. So it's pretty self-explanatory. It's 4. So 4 is the number of values in my type. But let's look at a more complicated example because there's a big thing that we're not seeing yet. Let's talk about geometry. Geometry, there's different types of shapes. So if I go type shape is equal to, it can either be a rectangle, and for a rectangle, let's imagine we're trying to calculate the area of a shape. Well, the rectangle, to calculate the area, you need 2 things. You need its base and you need its height. So we can do rectangle of double, double. Okay, so in this case, like we remembered, the asterisk is a tuple. So rectangle of a tuple. Now the of keyword is basically like a constructor. It's a constructor of an object. So to have this rectangle case, I need to have a double. I need to have a tuple of doubles. And also to make it easier, you can name these. So this can be height, and this can be base. And since base is a keyword, we're just gonna do that. Let's look at another example. We can do triangle. And triangle also happens to have the necessities of having the base and the height to calculate its area. So that's not very interesting, but let's say we have circle. So a circle, it needs its radius. You need a radius to calculate the area. And radius is a double. I notice I don't have to specify this. This is very, I normally just specify it when the types are very primitive or very basic. Normally, the best practice would be, like, let's say for rectangle, I can make a type that represents a rectangle here. So I can do type rectangle is equal to base, and base takes a double, and height is a double. And now we can do rectangle of rectangle. A few things happening here. First, you might feel this is kind of weird of having rectangle of rectangle, but we have to distinguish a union case with a type. This is a union case, and it's not a type. It's a constructor that will create a shape object. the constructor of this case takes a rectangle. Another thing to keep in mind is each of these don't have to take the same data types. So it's very, very flexible. And the actual implementation of this is shape is actually an abstract class in .NET, and its cases are concrete classes that implement the abstract class. So each of these has its own constructor. That's how it's done. And let's say I have a last one, and let's say my last one is a dot. So let's say a dot. Well, I don't need any data for the dot. It's a constant area. So I can just leave it like that. Now, if I'm going to write a method that takes a shape and I can compute its area, well, I can go ahead and do. Let's say I put it in a module because that's the best practice. If you're going to write a method or write a function that takes a shape or that acts on shapes, you probably want to group them together in a shape module. So I can do this and do let area shape. This can be done with pattern matching. Before I actually do this, I'm just going to do exception here. Before I explain how to do the area, I'm going to backtrack and explain what pattern matching is. And we're going to explain what pattern matching is on easier, like a little bit less complicated data types. So you'll have a nice leg up on the explanation. So let's look at Booleans, true or false. We haven't actually looked at an if statement yet, so it's a good time to do it. So let's say I want a function that's called yes or no. It has a bool, and I want to return the string yes when it's true, and I want to return the string no if it's false. So I can do if bool, then yes, else no. This is an if statement. If a condition, then something, else something. And since the if statement is an expression, it always has to return a value. So there always has to be a then, so the main case of an if, and there always needs to be an else that returns a value of the same type. That's pretty important. It's an expression-based language, and expressions should always return a value, except the let expression. And we can also write it, like this, I guess. But I don't really use if statements a lot because we have pattern matching. Maybe in this case, it doesn't make total sense. Like if it's a Boolean, maybe you feel tempted to use an if, and you can do that. It's not bad practice, but we usually use pattern matching. Let's look at the same expression, but with pattern matching. So match bool. If it's true, then yes. Well, if this is false, then no. So match something with, and then I have a sequence of patterns here. So I have a pattern. If the pattern is equal to true, then return yes, else, or in another case, if it's false, return no. So this is pattern matching. We tried to fit an instance into a pattern, and if that pattern match is successful, we return something. So there's a few types of patterns. This is a constant pattern. So it's a pattern with a constant value. So true. It could be 1 or 2, 3. Obviously, 3 doesn't work in this case. An int can never be converted to a bool can never be converted to an int. So it can't be like 2. It doesn't make sense. But true or false, they're expressions, they're constant expressions of the same type. So that works. And another way to write this, a point-free version with the function keyword. So now yes or no equals function, true yes, false no. So these two statements are exactly the same. The difference is that we don't have this bool variable in scope. So this returns a function. It's the word function. That's why it's the word function. It's a function that takes a parameter, and we do pattern matching on it. So when do we use the function keyword? You basically use it every time you do a pattern match and you don't need the variable. You don't have to have this variable in scope. Since it's very succinct, it's very easy to determine what's being passed in because there's only one data type that has the value true, and it's a Boolean. And same thing for int, and same thing for all the types basically. So it's a very good use of point-free code. This is basically writing this bool, and if I surround this with this and I go bool, and this is basically the same thing. So this is a function, and like all functions, I can apply it with a parameter, and I apply it with bool. Never do this. This is absolutely disgusting. I'm just trying to give you an example. So we can also do pattern matching on numbers. That's called isOdd. So isOdd number is equal to function. Actually, if I'm using the function keyword, I don't put the parameter there. So x, and the cool thing about pattern matching is you can add a conditional as well. So I can do x when x and the modulus of x is equal to 0. Then I can turn true. If you're putting if your pattern is a variable that you're declaring there, so x is not previously in scope, I'm putting it in scope in my pattern match, so it'll always be true. It'll always be a successful pattern match. But I add the when condition, so when clause. So my when clause, after I can put a Boolean expression. This is a Boolean expression because this is an operation on integer, which is the module, which division, and it returns the remainder of the Euclidean division. So in this case, if I divide it by 2 and my remainder is 0, it means it's a pair number. It's an even number. Actually, yeah, is odd. So this would be false. Or I can write it differently. I can do if it's equal to 1. So if the remainder is not 0, I can also do that. If the remainder is not, and not is like this in F#, 0, then it is true, which would mean the number is odd. So x modulo 2 is not 0. Yes, okay. I'm just checking my logic. There's a lot of double negatives here. I can probably just do is even. It'll be a lot simpler. So is even equal to 0, then true. All right, that's much more readable. In any other case, it's false. And the way we write any other case is with the discard operator, which is the underscore. And you can do false. So in F#, you can use the discard operator in in a lot of circumstances. And it's always used, well, it's used when you don't care about the value. And the simple fact of using the discard operator when you don't use the value, it makes code a lot more easier to read, because you don't have to look at a value that's unused and look, where is it used? Like, I'm confused. Someone defined a variable or a value and he's not using it. And that just causes brain, it kind of tilts you. So you want to avoid that. And obviously this is way overkill. I'm just using an example for the pattern matching. If you have a real is even implementation, you'd probably just want to do is equal to x. Is even x, then you want to do x modulo. Like, that's basically what you want to do. And like I said, you can use constant expressions like this, but let's say for int, if I had a method that's called is1 is equal to function 1, and it's true, else it's false. So like this will check if your input is exactly equal to 1, then it'll do true. In other case, it'll do false. And obviously, this is another case where you have a better implementation. Is one number is equal to number equal to 1, That's like a more smart way of doing that, and you can even take this one step further, and even a better implementation would be is one, and you don't really need this, and you can prefix this. We looked at pattern matching in not so useful cases for now. I'm just presenting these use cases because I feel it'll be easier to understand what pattern matching is used. Don't be worried if you think this is totally useless, you're never going to use it. We're going to ramp it up. We're going to ramp it up. It can also be used on strings. Let's say there's a common programming problem that's called FizzBuzz. And FizzBuzz basically asks you to print all numbers between 1 and 100 on the screen. And if the number is a factor of 3, instead of writing the number, you would write fizz. And if it's a factor of 5, instead of writing the number, you would write buzz. And if it's a factor of both, you would write fizzbuzz. So that's a pretty common problem. And let's say for an example, for pattern matching purposes, we want to do the opposite of that. The opposite meaning I receive a string, and if the string is fizz, I want to replace it with 3. And if the string is buzz, I want to replace it with 5. And if it's 15, I want to replace it with, or if it's fizzbuzz, I want to replace it with 15. It's kind of a dumb example, but it's just an example to show how you can use pattern matching with strings as well. So you can do let translate fizzbuzz, or I don't need to pass that, and is equal to function. So if it's fizz, then I can do 3, and if it's buzz, I can do 5, and if it's fizz buzz, I can do 15, and if it's not, and it's x, so it's anything, but I want to capture the value of what's been passed in, I can do x. But this won't compile. Why would it not compile? Because what's being passed in is a string, but all these cases return ints. So to rectify that, I'm gonna write all these as string, and this is exactly like doing a toString on the 3. So like I do 3.toString. But like this, you can. It's a lot better to have methods that don't use the dot notation, because like they're easier to compose together. That's why there's a helper function like that. Okay, so this works. So let's say I send this to the interactive. There you go. And I do translate fizz buzz, and I do fizz. I should get 3, and if I do buzz, I should get 5. Yes, and if I do fizzbuzz, I should get 15. And if I get tomato, I should get tomato. Good. This is actually a very convenient way of testing code with the F# interactive window. Now that we look at all the basic cases of pattern matching, let's actually look at the very neat, interesting cases of pattern matching. So we go back to this shape, which we want to calculate. So what do? Well, we can do a pattern match, that shape with, and now I can do rectangle rect equal to, and I'm just going to stop here for now, and I'm going to just copy this code over down here so we can see what's actually going on. So I'll write the implementation and then we'll talk about it. So it would be rect, it'll be base times rect height. Cool. If we do the triangle, so the triangle, which I defined as a tuple, so I can deconstruct my tuple like this. This is how I would use that, and we're going to talk a little more about that. height and base is equal to height times base divided by 2. Circle was a radius. I'm going to call it r. And it's actually r squared. R squared times math dot pi, which is the how you calculate the area of a circle. And then dot, well, we'll just say a dot has an area of 1. We went over a lot of things, and I just want to break it down. And before I do that, I should probably mention that to construct a shape, let's say I want to construct a circle, is equal, I can do circle, and I can pass in something. Like I said, each of these cases are constructors. So I can just give it, let's say this asks for a double, so if I give it a double, I get a shape. That's good. And if I do a triangle, I really suck at typing the word triangle. I can do, 2 and 4. This is a valid triangle. So notice how my constructor is also the same way I deconstruct something. So in other terms, the pattern to construct is the same pattern to deconstruct. And it's the same with tuples also. This is how you deconstruct a tuple, and that's how you also construct a tuple. And this applies for all F# types, which is really cool. So this rectangle, how do we construct a rectangle? We use the record type, right? Well, we can actually use pattern matching in this instance too. We can do base is equal to base, or b, and height is equal to h. And now I basically take the values of the rectangle and I put them in scope and place them in the, and I bind them to the name b. So I bind the base to b and I bind the height to h. So that allows me to use both of these, b and h. So I'm actually not only deconstructing the rectangle discriminated union, but I'm deconstructing its inner record type as well. So that's like super, super powerful. If I try, let's say I evaluate all of this. Okay. Now it's saying pi that's not defined. That's because when I added a math, I also opened the system namespace, which is on the top here. So I'm just gonna call it system.math, so I don't have to evaluate that top line. Okay. And now if I go area of circle, so I go shape.area. Yeah, it's actually pi. So this is 1 square times pi. So that works, and I can do the triangle. This should be these two, so 8 times divided by 2, 4. So if I do this, it's triangle. 4, good. So I don't have to use this shape because it's not in scope. You see, I only use it for the pattern match expression itself. I'm not using it for any of the values. So what I can do is, I can rewrite this. That's another way I can do it. And when you get used to this, it's just so much more fun to read, in my opinion. And this will work wonders when you're piping things together, because you can't use the pipe effectively when you're using the match shape with, because you'll have to use the fun keyword. Let's say we want to have really, really strong types, and I want to model a square. I want to add a square in this data structure. How would I do that? Well, a square is a type of rectangle, right? So actually we can write this type of rectangle differently. So we can have type rectangle, and I'm gonna have to fool around with names now. All right, so rectangle is equal to, and it's either a normal rectangle, normal. I don't have to specify the word rectangle because it's in the type name, so it's kind of redundant. And I'm going to call this a type normal rectangle. This is not redundant, so this is a normal rectangle. So it's either a normal rectangle of normal rectangle, or it's a square. And if it's a square, I only need one side. So I have side, and that's a double. Now I simply need to update this. Since I renamed it, it also renamed it here. I actually just want a rectangle here. Now the first thing you'll notice is that now my patterns don't work. I can do, call this a rect. And this is a rect also. And in my rectangle library or something, I can do a module rectangle. And I can do let area of this. I can do pattern matching here. So if it's a normal, and now I can deconstruct this. So base, we can do b times h. And for my square, I can do s for a side, and I can do side times the power of 2. Okay? So that's great. Now I have my rectangle function, and I can just call rectangle dot area on rect. So that works. And I'm just going to remove this for now. Okay. So you see I can just add a new behavior like that and very specific types for my data, and it makes it, well, in this case there might be not a massive advantage. In the real world there can be a massive advantage of having very specific types. And we'll see one with our, we'll probably do a FizzBuzz exercise, and we'll see how specific types help to reduce the amount of unit tests you need to do and remove the amount of type checking and not null checking, but data checking and validation. Also, I mentioned the word null. I haven't used the word null here. I haven't talked about the word null. Null is not really a thing. Well, it is a thing in F#, but you never see null because you can't instantiate something to null unless you explicitly say it can. An important detail to mention with pattern matching is not only we can use it in the match expression, but we can use pattern matching in the let and fun expressions. So let's say I was doing another method to calculate the area of only a normal rectangle. So I can go let area, and I can deconstruct my record type because I'm going to pass this in. I'm going to pass a normal rectangle in. So I can go ahead and do base is equal to b, and height is equal to h, and then I can just return b times h. I'll put it on another line, but pattern matching in let expressions is very powerful. And the same can be done with the tuples. So if I do let area prime, and let's say I get base and height, I can do base times height. That's another example. And one thing to keep in mind is why can I do this in a let expression? Well, I can only do it if there's one case, if there's one pattern possible. This works with single case pattern matches. So examples of single case pattern matches include record types, tuples, and single case discriminated unions. Let's say you have an ordering mechanism. Ordering, you have products and you have orders, and each order has an ID. to identify what it is, right? And we don't want, we can use int as an ID, but the problem is it doesn't really document what it is. It doesn't really document that the integer represents my order ID. So a common practice in F# is to write wrapper types. So let's say in this case, type order ID is equal to order ID of int. Okay, so this is a single case discriminated union. Like you can imagine if I wrote it like this, right? It's a discriminated union, but it only has one case. And so in this case, I can, let's say you want to increment the order ID. So you can do increment order ID. You can, you normally do order ID equals to whatever, right? Well, how you access this value? Can you dot in? No, you can't dot in. The way you access it is by deconstruction, as we talked about. So you can deconstruct it in the let here. So increment ID, order ID, let's see, it represents this, of int, so this is an int. And I can just do return a new order ID that has, and actually I'll write it correctly. So ID plus 1, and I can pipe it into order ID. Right? So we do ID, we get the ID, we do plus 1, and then we pipe it into the constructor. Now, although I did mention that we want our code to be read in the same order that it is executed, there are some exceptions that we can playfully entertain. One of the most popular ones is when you're constructing discriminated unions, it's nice to have the name of the discriminated union on the left and having what's passed in on the right. But the problem with that is if I do this, now this doesn't work because this is an expression. It's not a value. It's not one value. It's it's its own expression. So I have to surround it with parentheses. So that works, but another common way, because for some reason I don't like parentheses, and a lot of people don't like parentheses in this context. So you can do the reverse pipe operator. And this reverse pipe operator basically applies an expression on the right to the left. So it's the same thing as this. Like I just said. And conversely, if I didn't increment, if I just passed the ID, this is exactly the same thing as this. So it's really not a big deal to me and to people in the community to have that reverse pipe. Don't abuse it, of course. Like we don't want to just spam it where we can, but it can help to read. So we can also rewrite this expression to show how we can deconstruct with the fun keyword, which is the Lambda keyword. So I can do increment order ID prime is equal to a function that takes in an order ID, but I want to deconstruct it here. So instead of writing order ID, I'm going to write parentheses order ID, and I'm going to make it equal to this. I'm just going to rewrite it. So these two are equivalent. I'm just showing you that you can pattern match on parameters passed in the Lambda expressions. So now that we looked at a little bit of what a discriminated union is and how to use it, we will move forward with, it's a type of discriminated union that we use to represent optional data. And this is the replacement to null, basically. So in other languages, reference types can be nullable, and so they can either have a value or not. Like they can either point to something real or they can point to nothing. And this concept is represented by the option type. So the option type let's like define it. Option is generic, which I'll talk about. And it's either sum of A or it is none. So it's either some or none. And there's a lot of advantages of this over having nullable types. The first one, the biggest one, is no more null reference exceptions like ever. Haven't had one in F# since I started writing F#. So that's like really a cool thing, and it clearly documents whether something can be there or not. If it can have a value or not. I won't talk about generics for now. I'm going to talk about it in this video, but just not for now. So for now, just look at a generic as a generic in any other language, basically, in C# or Java. Let's look at an example where options make sense. And let's scroll up back to our translate fizzbuzz problem. We either want to, we want this function to return an integer. Right now it returns a string, but I really want this to return an integer. Okay. Now, in the cases of fizzbuzz and fizzbuzz, that's great. But what happens in the case of it's not any of those? Normally, in any other language, you would do one of two things. You would either return null, and we don't want that. Int can't be null. The other thing we might want to do is throw an exception. And in F#, for now, we're going to do fail with and give a message. Normally, you just use invalid arg, but I'm just going to do this quickly. But we're going to talk about exception handling in a little bit. It goes against what we want. We want we want to clearly document what can happen here. And right now, with this type signature, string to int, it doesn't really clear document what can happen normally. And we have to distinguish some errors are domain errors in the sense of they're errors that are predictable, they're unhappy paths. So for example, you're doing a banking application and you have a function to send money to someone else. Well, if the money you want to send is bigger than the money you have, then that's a classic example of something that can happen. It's not super exceptional problem. It's an error, but it's an error inside of the business rules of the business. The business rules are you can't send money that you don't have in your account. And those kinds of errors, they're not exceptional. They're not exceptions in terms of how we want to model our functions and our data. Well, the example I just listed is more of a result type, which we'll get into, but optional types are a bit the same. Like, you want to parse an integer out of a string. It might not be, the string might not be an integer, but normally in C# you would throw an exception and say, invalid argument. But in F# we can use the optional type. And in this case, like we're parsing this string here, and instead of doing this, what we can do is we can do sum 3, sum 5, sum 15, and if it's not any of those three, we can do none. And this compiles. So we'll say that it's an option. I'm just going to remove this because option is a base type, and you can read it this way. You can put option at the end of the type, like here. It's not option of int, it's int option. It's just another way to say it, or another way to write it, rather. So here, we perfectly document that the result of this operation might not give a value. It might be incorrect. And let's say if I wanted to use an option, if I want taking an option, I can do let is sum, so or has value. Probably is sum is the best way, but for or has value to make it easier to understand. Has value equals function equal to sum of anything and that returns true because I just want to check if my option has a value. So I can do some of that, and if it's none, then I can do false. So that's an example of using an option. We often use option with the pattern matching. Now, a note on generics. You can see that this last method takes an A option and returns a bool, because we don't really care what value it is. So in F#, with the power of type inference, we can implicitly say that things are generic, which is really cool. And that's why we had the A when we saw the type annotation. The type parameter is the correct word for the option type. It means the option type doesn't really care what the value is. And so this is a generic type at runtime. And so there's a few differences because there are statically typed or statically resolved type parameters, and there are dynamically resolved type parameters. And this can be like a very long topic, but basically when you see a prime, when you see the prime, it means that it's dynamically resolved. That's one of the things. And statically typed type parameters, I'll give you an example. I never really addressed the fact that it takes int as a parameter. Why? So I avoided that because this is a classic case of statically resolved type parameters. Statically resolved type parameters permit the use of adding constraints that are based on members of a type. So I'll show you what I mean. We don't see it like this because we have to use the inline keyword here. Now you see it's a I actually don't know what the character name is in English. Caret. I'm French. So what does this mean? Well, if we mouse over add, it'll say it's an A that returns well, X is an A and Y is a B, and it returns a C. And they require member plus. So that means that on the types, they require a member called plus. And I didn't really talk about this yet because I don't want to go too much in depth, but you can specify members on types. And a classic example of this is, let's go back to a person. I can do type person this, and I can do with, and then I can do static member plus P1 and P2, and I can do, break these down. So we do name equals N1, age equals 8-1, and now I can do, I return a new person, which has name equal to N1 plus N2, and an age equal to A1 plus A2. And now I get an error. It's probably going to tell me to use these as tuples, yeah. So we can define them as tuples. And that's basically overriding the plus operator in C#, in F#. So I'm just adding two people together. So with this, I can actually use this generic for person because I defined, so this statically resolved type parameter was requiring the member plus in order to be used. So I can actually do Ben plus Alex now. This compiles. If I don't have that up top, and I save, I'll have an error at the bottom and say this does not work because it says person does not support the operator plus. To have access to these statically resolved type parameters, you have to use the inline keyword. And the inline keyword is you're recommending the compiler, but not the obligation to copy this code instead of calling this function. So basically, the inline versus non-inline. So let's say this is inline, and I do a non-inline version, and I call it prime, and I do add 3 and 5, and then I do add prime 3 and 5. In the first case, what it will do is when it compiles, it will actually just be written this. It won't be a method call, as opposed to when this is compiled, it will actually do a method call, and it'll do 3, 5. And so there's a performance benefit to that, and it's a lot easier for the compiler to check statically resolved type parameters if code is inline. If there's a lot of redirection with method calls, it's a lot harder to do that, so that's why it requires the inline keyword. So I'm going to move that to the side for now. And generics are important for my next topic, which are collections. There are 3 main types of collections, of ordered collections. There's obviously way more types of collections, like maps and sets and dictionaries and stuff. We're not going to go through those for now. We're just going to talk about ordered collections, so arrays and lists and stuff. So the first one is the array. So arrays are exactly like arrays in C#. They're the same thing. They are fixed size, but they are mutable. And the way we define arrays is with the square brackets and the bars. So the same way that anonymous records are curly braces and bars, arrays are square brackets and bars. And we can define an array with the semicolons. Like we said, the semicolon is an expression separator, much like the new line. So we can do new line as well to do 1, 2, 3, 4. And we also have a range operator, which is very nice. So if I do 1 to 10, I can do 1.10. So this will give me all elements between 1 and 10. Just give it a name and give it R equal to this. I can change the value of my first element with the dot accessor. So this is how you do it in C#, like the first element, like this. But in F#, you have to use the dot before it. And I can, like we said, mutate it. This is the assignment operator. I can give it 5, like a big band man. And if I reevaluate this, it will see 5, 2, 3, 4, whatever. So that's not fun. And you see even here, when it printed it out, it was already mutated. So if I do it like this, it's fine. But then if I do it like this, well, now it just does it. Now if I do it everything, I'll do 5. So even though there's a lot of benefits to arrays because they're fixed size and they just allocate one big chunk in memory, it's not the preferred collection we use in F#. The preferred collection we use in F# are lists. Lists are immutable. They're fixed size if they're immutable. It's actually a linked list. It's implemented as a linked list, as opposed to a list in C# is an array list. We basically never used array lists in C#. It's called a resize array, but we never use it. It's used sometimes, but it's not recommended for most purposes. So we can use exactly the same things for the list, for the array on the list. So this creates a new list, 1, 2, 3, 4, 5. That works, and we can also use the range accessor. 10. And the range accessor is very nice as well because you can actually define an increment. So by default it increments by 1, but if you wanted to increment by 2, you can do 2 and then dot dot again. So that will give me all the odd numbers. That's very nice. This also works with doubles, the increment. So I can do 0.1. I have to do 0.1 probably. And I can do dot, and I can do dot. So now there's a lot of dots, but you can separate them with spaces if you want. and it'll give me a lot of numbers. So that's fine. These are generic, so you can do whatever you want. A to Z. So the big benefit of using the array is random access. So if you want to access the, let's say 50th element of a list, of a collection, you probably want to use an array, because for a linked list you have to start from the start and go in each node get the next one until you're at 50. So that's a big difference. So random access is a lot better with arrays. In any other case, lists are pretty good as well. Now the beauty and why I talked about discriminated unions before I talked about the collections, because normally collections, you want to know about them very early in the learning process. But there's a specific reason why I postponed this, and it's because I want to show the implementation of like what a list looks like, this linked list. So this linked list of A is equal to, so it's either an empty list or it is cons, so this is cons, head, which is an A, and tail, which is an A. Okay, so let's break this down. And this is basically defining what list is. So a list is either empty, so you can create an empty list like this. This is a constructor for an A list. The other case is what we call the cons operator, CONS. And it's a Lisp term for constructing, I believe. I never done Lisp, but that's what I saw at Wikipedia. And this takes a tuple. I can do let's add to list, and I want to add X, and I wanted to add it to a list. And basically I'm gonna use the word XS because XS is the it's the common term for a tail of a list. So X and XS is two things you want to remember. So if I want to add X to XS, I do X dot dot XS. So I take an A. This ain't good. Add to list. I take an X and I get an A list and I return this. Obviously, I'm gonna just remove this. I'm just gonna put it in comments because it's distracting. Yeah, because I was accepting an A list and returning a linked list when actually I just want to take a list and return a list. Okay. So what I'm doing is I have an A list and I'm constructing a new one with this operator by appending X to the front of it. So let's look at a concrete example. Let's say I have 2, 3, 4, and I'm going to call add to list. I'm going to add 1 to, and I'm just going to call this let sample list. And I'm going to add sample list here. And I'm going to define this. There you go. So I add the 1 in front, and it returns 1, 2, 3, 4. And what did we see about discriminated unions in the past? We saw that the constructor pattern is the same as the deconstructor pattern. So let's say I want to get the first item of a list. Let get first item of list is equal to, how do I get the first item of the list? Well, I can deconstruct this XS and return X. This is the beauty of the compiler. It tells me, hey, there's an incomplete pattern match. It says you didn't match all the patterns because we forgot this empty pattern. What happens if it's empty? So we can't use it like this. So we're going to pattern match. And I'm going to say if it's an empty, I'm going to say if it's X 2 dots blank, because I don't care about XS in this case. I just want to get the first element. I'm going to return x. And if it's not, well, I should probably return an option. So I'll return an option here because it can be empty. And if it's anything else, I'm going to return none. This is an example of using the deconstructor of a list. So a lot of the types like option, list, array, they all have a lot of methods I can use that are built in. So you don't have to implement a lot of this logic yourself. And in this case, we talked about get first item. This is also referred to the function head, the function called head. So get first item, I have a list here. I can just call list with a capital L, which refers to the module. And I can just do head. And I'll return a T. So this one, we'll throw an exception if I have an empty list. If I just try it out, if I do list.head and I give it an empty list, yeah, it's complaining because it has a little bit of trouble with the type inference. So let max equals to this. Even though the list is generic, each instance, the instance has to have a type, the type parameter. So an instance cannot be a list of whatever. An instance has to be a type of int, it has to be a type of float, it has to be consolidated. So that's why the compiler is annoying me. So I can do x is int list. And this will compile fine. And now it will throw. It'll say the input list was empty. So that's how it's implemented by default in .NET. Forgot to put the word list here. Okay. Now let's say, for example, you want to perform an action on every item of the list. One way we can do it is with a for loop, right? So we iterate through the loop. For every element, we print it out. And that's normally the imperative approach. In functional programming, there are two other approaches to use. And one of them is with tail recursion. Tail recursion is a form of recursion that basically, if you write your recursive methods in a certain way, the compiler is going to optimize it to transform it into a tail loop, into a loop. So let's have a function, let print every item. And it will be a pattern match. So I'll do function. And if I have xs, so this basically means if I have an item, if there's an item in my list. Because this will always match if it's not empty. I want to print, and I'm not sure what the data type is here, so I'm just going to do print %o, which means it can be anything. It can be an object. And I'm going to print fn. And after that, I want to do it for every other element. So what can I do? I can actually recursively call this method. So I can do print every item. And it says that it can't do it. Well, first I have to add x here. So it'll print the object. Now it says it's undefined. Well, we can solve that by using the rec keyword, which will enable us to use recursive methods. And if it's an empty list, what do I want to return? Basically, the printing operation is a side effect, right? So we want to return unit to document that nothing is returned here. Okay. So the function signature takes an A list and returns unit. That makes sense for us. So if we go ahead and try this, print every item, and we'll try it with 1, 2, 3, 4. So we will send it to the interactive. 1, 2, 3, 4. Great. We have a behavior here, and it's kind of hard-coded. We can easily extract this logic and pass it in, is what I'm trying to say. So instead, what I can do is, instead of print every item, let's call this do with every item. And we'll give it an f. we'll give it as a parameter, it will take an f. So we'll take an f and it'll take a list. And what is f? Well, it's basically a function. I'm not going to give it a type. The compiler is going to help me with that. So instead of printing here, because printing is a function that took an object and returned a unit, I'm basically going to do the same here. So we're going to put f here, and it says that f is in A and returns a unit. So that's exactly what I want. And I'm going to call this here. So I have to repass f. I can reuse this. It's very reusable. If I wanted to print every item now, and let's say I have let print every item prime, I can do every item, and as a function I can pass printf O, right? And I can pass list here. With this function do every item, I can pass a function that takes an object and returns unit, which is this. I can also write it point free. So I can only write it this way. I can also write it this way. So we have to decorate it with the type parameter just to give it a little bit of help. If we don't put it, we can just do this, and what that will allow us to do is it will give an A list here. It's basically just a little detail. So maybe that's a good reason to add the word list, just to make it less ugly. So this behavior here, we don't have to re-implement this. I just did it for the sake of explanation, but this is actually the list.iter method. So list.iter is for loop. It's basically for each. So for each, you give it a list and you give it a function. That's basically how it works. Normally how you write it is, how you use it, is you would do this. You do list, pipe, and then this. So you have list, iterate, function. That's basically how it's written. The next method that we'll see a lot of is, I'll give the example beforehand. I have a list of integers, so 1, 2, 3. Actually, you can just do, I want a function that takes in this list, or a list like this, and returns a list of a list of strings that look like this. 1, and 2, all the way up to 10. Again, you could use a for loop or something like that, but we have a method that's called list.map. It's the mapping operator, and map is very prevalent in functional programming. So let's do stringify list, and I have a list here, and I'm gonna do list, and I'm gonna pipe list.map, and the function that will take an integer and convert it to a string is actually the string method here. And it says I have an object list and it converts it to a string list, which is fine, but if we want to add a little bit more specificity, if we want to add a bit more specificity, you can do int list here to tell it that list is an int list. That's great. Other way, we don't need to add that, so stringify list. And I'll give us all the stringed elements. It's not only the list that has this operator, it's actually a lot more data types. For example, the option type has this. So if I want to use the same concept, let's say I have sum 42, let's say, and I want to end up with sum 42 in a string, as a string. Well, I can basically do sum 42, pipe that into option.map. Oh, I have to give it a function, yeah, sorry. And the string function, I'll get sum 42. So map is also known as select in C#. I should probably mention that earlier. If you ever done LINQ in C#, it's basically your bread and butter. You will always use select. Now that we talked about map, let's talk about fold. fold is a little bit more complicated, but nonetheless it is very useful. I have a list of integers, and let's say 1 to 10, and I want to get the sum of the list. So I want to add all the items together and get a number. We can use list.fold. And I can do list, and then I will fold. And fold is aggregate in C#, which fold takes a function that has two parameters, x and y, and I'll call them accumulator, and I'll call this one current item. And then it takes an initial value. So in this case, it's 0. So on the first iteration, my accumulator is 0. My current item is 1. What we'll do, we'll add 1 to 0. So on the next iteration, my accumulator will be 1, and my current item will be 2. Now I'll add those two together, so my new accumulator will be 3. And my current number will be 3, and I'll add those two together. So basically, folds an operation together. It's basically like you're rolling up, like your list is a blanket, and you're like rolling it up, you're folding it. In this case, we can write it in a much more convenient way and do, we can do the plus with the prefix notation. So plus is a function that takes two parameters, so that's good. And in this case, the accumulator and the current values are the same type. They're both ints. This won't always be the case. So your function might be different in those cases. So that's kind of a brief overview of fold. It's a little bit more complicated, and you know, it has its own uses. So I'm going to just leave it here for now. Another way to write this is with the reduce method. Let reduce list is equal to list dot reduce, probably wanted this before, list, and we'll pipe it into reduce, and we'll give it a function. So reduce takes a function, much like the fold takes a function. It takes a function of two parameters of the same type, then it takes a list of that type and returns a final value. So it's basically fold, but there's constraints. The accumulator needs to be the same type as the type of every item in the list. So if the list is an int list, then your accumulator, if it's an int, then you can use reduce. As I'm recording this clip, I'm not satisfied with the way I explained reduce, and it's two constraints. The first constraint of reduce is, in order to use it, the type has to be able to combine itself with the addition operator. So in this case, two integers with the plus creates a new integer, which is the combination of the two. So that's the first constraint. It has to be combinable. The second constraint is it has to have a 0 or an identity value, which when you add the 0 to another value of its type, it returns that value. So in the case of integers with the plus function, when you add 3, when you have a 3 and you add 0 to it, it returns 3. Another example is the multiplication. So if you want the product of all the elements of a list, the 0 for the multiplication function is 1. Because let's say, for example, you multiply 1 by 3, it returns 3. A type has to have those two constraints in order to be able to use the reduce and the sum functions. And now, back to your regularly scheduled program. For integers, we can just use the list.sum list, and we can actually just use the list.sum function. So that works for us. This doesn't work with generics. Maybe if we inline it, it'll be fine. Yes, because it's a statically resolved type parameter, and it requires two members. It requires a plus member and it requires a get 0. So in this case, if I had numbers 1 through 10 and I use the sum prime prime, it'll give me 55. Is that good? 11 plus every item's 11, you need to have 5 times, yeah. Okay. So that's fold, reduce, and sum. Now I want to talk about bind. Let's say I have a function that takes a number and divides it by another number. In this case, if it's not a natural number, if the result is not an integer, let's say, so it's a double, like let's say the result is 1.5, I don't want the result. I only want the result if it is an integer. And I'm going to give it a nominator and a denominator. I'm going to do some pattern matching here. So I'm going to do match nominator divided by modulo denominator. If the result of this is 0, then I will return sum nominator divided by denominator. If is not the case, so if it's anything else, I'll return none. So this is basically saying I want to divide two numbers and I only want the result if the result is exactly an integer. And to make things easier on me, I'm just going to define a function that is divide by 2. Divide by 2. And this will be equal to divide integer, and I'm going to partially apply 2. So my denominator is 2. So this function takes an int and returns an int option. Okay, so let's say I have sum 24. And let's say I now divide it by 2. What happens here? My function, it takes an integer. It doesn't take an option, right? So let's say in this case we start off. Let's say we start off with an integer, and we pass into a function. It gives us an int option. Well, let's say I want to divide by 2 again. Well, there's a problem here because I'm receiving an int option, but my function is actually, it takes an integer. It doesn't take an integer option. And I only want to execute my function if I have a value in my option. So if my option, its value is none, I don't want to execute my code because I'm not going to divide none, right? So this is where bind comes in. So option.bind, it takes a binder, which is a function that takes t to u option. In this case, they're both ints, so it's int to int option, and it takes an option in, and only executes your function if it's sum. So let's actually write the implementation just to help us visualize it. So let bind is equal to bind f, because we take a function. If it's sum x, then I want f x as my return value. If it is none, then I'm going to return none. It's an A to B option, and I give it an A option, and it returns a B option. So this is very practical. When your functions, they take values in input that aren't options, and they return optional data, and you want to chain them together. The bind function chains them together very well. Probably have to do this. Okay, now I have sum 6. Let's divide it by 2 again. What do I get? I should get sum 3. Okay, what happens if I divide by 2 again? 3 divided by 2 is 1.5. So I get none. So that's the beauty of bind. It helps plugging functions together that normally don't fit. I briefly mentioned it, but a lot of these functions are found, so a lot of the list functions, they are found with arrays as well. So we have list array dot all of this. So we have fold, you have empty, find for all, get, item map. There's a lot of versions of map, length. A lot of these functions, they all have the shared functions together. So that's great. So exceptions. Like I said, exceptions, I said previously when we talked about options, we prefer not to deal a lot with exceptions in functional programs. That is not to say they're never used, but the exceptions are used when there are very exceptional problems, like you can't connect to a network, or there's a programming mistake that raises an exception, that's fine. But normally for domain errors in a business context, errors in the business context where, let's say you order a product but there's no more products in the warehouse, so that's an issue you have to handle, and it's not exceptional. That will happen. That's part of the flow of the business rules. And so with these types of errors, we don't want to use exceptions. For exceptional workflows, we want to use exceptions. And so we can define new exceptions with the exception keyword. And we can do cannot connect exception. So that's how you define an exception. Keep in mind, exceptions in F# defined like this are very lightweight. You can't add an inner exception to the exception. So normally when you raise an exception, you can pass the inner exception. You can't do that. You can't by default set the exception message. So these are two very big limitations of this style of exception. So we can actually use these exceptions. How they're more commonly used is a little bit like union cases, like error union cases. So let's show an example function that's called handle, and it takes a function, and this function, we know it might throw, let's say. So we want to catch this exception. So we can use the try keyword, and we will call the function. And so in F#, it's not actually try catch, it's try with. Try with, and then we define a list of cases. So exception cases. And so for the F# defined cases, we can actually just directly write cannot connect exception. And then we can choose to do whatever here. For now, we can just do nothing. And this compiles. So we have a unit to unit function, and it returns unit. But for, let's say, .NET exceptions, we can't directly use this expression. We actually have to cast it. We have to ask, is it of some type? So we can actually do, this is a cast. We're trying to cast what's been inputted as, let's say, system.argument exception. And we can do it as E. So what does this mean? We're trying to cast the exception, and if it's a successful cast, we put the exception into E. So here we can do print fn, and we can print the error message, let's say. That's another thing we do. So that's a little bit how exception handling works with the try with. So we can also raise exceptions with the raise keyword. So it's not throw in F#, it's raise. And we can do cannot connect exception, for example. Another big thing with this is we can actually accept data, like a union case. So if cannot connect, we want to have a URI, let's say, that we can't connect to. System.URI. That's one thing we can do. And we can put this URI into context. And we can do the same thing here. We can do URI. So this is kind of ugly, but it's just an example. And you can give data, much like a discriminated union. But instead of exceptions, what we normally focus on is we actually model errors with discriminated unions. We talked about the bank account earlier. You're trying to withdraw money from your account. We want to model what are the possible errors of that operation. We can define a new type called withdrawal errors, and this is equal to this insufficient funds, let's say, and let's say you can take amount of money. We can try maybe a wrong NIP or wrong PIN. So that's kind of how you want to model your errors. And when you have a function that, it can either return a good value or it can return an error, it's basically like the option type. You can have more information in the error cases. And we use the result type for that, which already exists. So I can do let result is equal to error and insufficient funds. Since this takes a double, I can do 10. So we have a result of type whatever, and we know the error result is withdrawal. And to better illustrate what the error actually is, we can just define what the result is. So it's a case that's either OK of type OK, or it is an error of type error. But let's compare the definition of this type with the definition of the option type. So these two are very, very similar. The only difference is that the error clause, or the error case, contains data. That's basically the difference between options and results. But they're much more powerful to document what possible errors you have. And we'll be using results in our example application, which we'll be doing in the next video. So I'm going to end it here for the day. We went through a lot of content, a lot of the language itself. We have a lot of the basics down, to be honest. We looked at the primitive types, we looked at let binding, we looked at functions, we looked at currying, we looked at function composition, we looked at namespaces and modules, we looked at how to create your an application with the main function in your console application, and using the console itself. We looked at the the unit type and what it does and how it documents purity and impurity. We looked at types like record types, tuples, anonymous records. We looked at discriminated unions. We looked at pattern matching, a lot of pattern matching. We looked at collections, recursion, main functions or higher order functions that are iter, map, fold, reduce, bind. We looked at the option types and the result types. We looked at error handling. So we have a lot of concepts down. You can write your own application right now with these concepts. There are still a lot of concepts we haven't gone through, and I'll be planning another video for that. It won't be next video or the one after that, but we're going to look at sequences, which I didn't really talk about. Sequences are lazily evaluated collections. They're basically IEnumerable from C#. We're going to look at computation expressions. We're going to look at asynchronous programming, active patterns. There's a lot of stuff that I haven't talked about. Units of measure. There's a lot of really cool language features that I didn't feel were like necessary, like completely necessary to write a basic application. But that doesn't mean they are by no means useless features. They are super important. But we're going to talk about them in another video. I think probably I don't know how long this video is actually going to be. It's probably going to be a couple hours, or maybe 2 hours, maybe 3. I don't know. So I hope you enjoyed this. And in the next video, what we're going to do is we're going to write out an enterprise-ish enterprise-ish version of the FizzBuzz program. And we're going to look at how we should build an application and how we should respect the proper software designs and proper the best practices of how to design software in F#. So that's going to be a hands-on tutorial, a little bit like this. It'll be less draining on the brain because this is basically a brain dump of a lot of concepts. And next video we're going to actually use the concepts, and you're going to see how they actually relate to each other and when they're going to be used. And so that's going to be very, very fun. And so we're going to do that in the next video. And then the video after that, we're going to compare the FizzBuzz application that we're going to do. And we're going to compare it with a C# implementation and see how those two implementations differ. And we're going to drag a lot of insights of what the differences with the languages are and the paradigms are. Because the C# implementation will be a 100% object-oriented implementation. I'm not allowed to use lambdas or LINQ. So we're going to see a lot of the differences with that. So just to make sure that the following, the part 2 of the language tutorial is going to be in a few videos. It's not going to be immediately the next one. So make sure you're subscribed if you want to see more content like this. And make sure you like the video if you enjoyed it. And if you have any questions or anything that I got wrong, or any like, oh my god, how did you not go through that? Just make sure you leave a comment, and I'll make sure to address it. So thanks everyone for watching, and we'll see you guys in the next one.